Hello, everybody, and welcome to this last session of the year, where we are going to talk a little bit about the last exercise for logic now, and then we are going to continue with probability theory, where my colleague Josefina is going to take over. Merry Christmas. As you can see, I'm not at the university right now. And this is a little bit of a technical problem because I don't have the iPads that we typically use at the university to show you the notes. So I still have something that I can show you the exercises with, but when I'm going to upload the slides, they might have a quality which is ever so slightly worse than with the iPad. So I just wanted to give you a heads up here. I'm still going to upload them, but then when I'll be back in Munich, I will upload them professionally, so to say, and then yeah. But for now, you will get still the slides, but a little bit worse quality. Anyway, so last time we talked actually about backwards chaining. We looked into detail how to use the algorithm, and there's a small little point that I want to talk about. So last time there was the question of how do we know which rule we have to use, right? Because at the start we started with rule 8, which is this one, right? Then we used, I think, rule 4, something like this. And somebody asked, okay, how do we know which one we have to choose? And I said last time, okay, this is a little bit, this is practice. There is no general way of 100% taking the right rule each time. This is true in general, but typically there are a few things that you can see, okay, I actually need to use this or this. If I use this, there's no way that I can identify my sentence. So to give you just a little bit of an example here, so we started with this goal that we wanted to show, right? And there's pretty much only rule 8 that we can use here, because you can see here, okay, if we have to identify the right hand side of rule 8 with that one, it works because we can just replace x by 7 and z by 3 plus 9. Whereas if we do that with other rules, for example, rule 7, then sure, we can do the same with y and z, but we can't really do it with w and x, right? Because w, perhaps you can choose 7, but x, what is x then? I mean, sure, you can say, okay, in theory, there should be a +0, but that is something that we interpret, right? A computer would not be able to interpret that here. So here it doesn't work. The same for rule 6, you cannot identify it. Rule 5 also doesn't work, for neither does 4, 3, 2, or 1. So here it's pretty obvious that you can pretty much only use rule 8, and that's it. So yeah, typically you kind of see with what you can identify your goal with, and that sort of gives you an idea what's to use. Okay, is this for today? Yes, I mean, today is the 23rd. I'm not sure what that question means, but yeah, feel free to specify. Okay, so now that we have talked about this exercise, let us actually go to the actual exercise that interests us this time, and it's going to be about first-order logic resolution, right? And there's going to be this interesting problem of the man in the painting. So basically, there's a guy which is drawn on a painting, and another person that looks at the painting and says, "Brothers and sisters have I none, but that man's father is my father's son," which is a relatively easy sentence, but we will see that this can be a little bit problematic. And to understand a little bit what's happening in this exercise, we are going to formalize a few sentences, right? Because that's what we're here for. At least that's what I'm here for, transform everything into first-order logic. So we have a couple of predicates that we can use. If somebody is a male, if somebody is the father, somebody else, somebody is the son, the parents, the child, or the sibling. Okay, and we're given a couple of rules which are already formalized. namely this one, which just defines what a sibling is, and this one which just says that if you are a parent of somebody, then that somebody is the child of you. Okay, that's relatively straightforward rules. We just gave them right away because they can be a little bit tricky to formalize. So yeah, there's enough formalization to be done in this exercise already. So yeah, those ones are not necessary. Okay, we do, however, have some stuff to formalize. Let's start with this sentence. Every son is a male child and every male child is a son. Now you can perhaps already see that in the construction of the sentence, you sort of have something which happens in both ways, right? So you have every son is a male child and every male child is a son, okay? So this is typically a very strong sign that there is, actually, let's make the pen a little bit small. So it's typically a very strong sign that actually here we have an equivalence here. And it also makes sense because we are sort of defining what a son is, okay? And when you define something, you can typically do it with an equivalence. All right. So what do we have here? We are going to have a son. So we need to check if somebody is a son. And of course, if we want to check if somebody is a son, well, we can't really check if somebody is a son without a father being involved, right? So we actually also need yet another variable, which is going to be the parent in this case. Parent or father, doesn't matter. You can also call it F if you wish. So as I said, we are defining what a son is. So let us write this thing down. And so a person is a son of somebody else if and only if that person is a male, okay, is a male, which is here, and is a child of that person. So literally, and is child of that person. And that's pretty much it. We can also put some brackets so as to avoid confusion. And yeah, that's pretty much it. Easy sentence. We can go to the next one. That's going to be relatively similar. We also have every father is a male parent and every male parent is a father. Okay, so what are we going to have here? We are going to have, so a child and a parent again, right? So this is going to be a child. And this is going to be the father in question. The father that we are talking about. Okay, so as I said, we are defining what a father is. Let's just write it like this. So if somebody is a father of somebody else. Now again, for the same reason as above, we are using an equivalence here. And then we are saying, okay, a father is a male. Okay, so let's check if it's a male. And it needs to be a parent. So parent of C. And that's pretty much it. That's the first two sentences that you have to formalize. Easy enough. Then we have two other sentences that are relatively easy to formalize. Namely, we have to say that the me speaker and the that on the painting are both males. So let's just write that down. Okay, male me and male that. And that was it. We're finished for those two sentences. Okay, let's go to the next one. Those ones are a little bit more tricky. So we have to formalize first, brothers and sisters have I none, and the I here is the me speaker, right? Okay, I should go back to slide 611. I think that's that one, right? I think some people are writing it down. Yeah, okay. Then let's continue with that one. Brothers and sisters have I none. In other words, the me speaker does not have any siblings, right? Because we don't have, we haven't defined brothers and sisters. We have only defined siblings, but that's fine. That's more than enough for our case. So what we do here is, since we I already know that I need to transform everything into conjunctive normal form, right? That's why I'm going to simplify my life a little bit, and I'm going to write it in a certain way that makes it directly obvious how it is in conjunctive normal form. Namely, if I say, okay, he has no siblings, it's the same as saying for every person, that person is not a sibling of the speaker, right? So for every person, it's not a sibling of me. Here we go. Now here we need to be a little bit careful because sure, here I have said that that person is not the sibling of me, but since sibling is sort of symmetric, we also need to add it in the other way. X. Here we go. Just, yeah. We could also define a specific rule that would say that sibling is symmetric in that sense, but yeah, we didn't want to go through the trouble of that. So yeah, this also works. Okay, now the last sentence is a little bit more tricky because so there's a little bit easier way to analyze this. So we have two people involved actually here. We have that man's father. Let's call that person T1. And we have my father, right? Those are two people. Let's call it T1 and T2. And now, what do we know about those two people? Let's formalize just those things, right? So that man's father. So T1 is the father of that. Okay. So I can write, okay, father T1 that. Okay, fine. Then T2 is my father, so it's the father of me. Okay. T2 is the father of me. And finally, the thing that we know what connects T1 and T2 is that T1 is the son of T2. Okay, so I write this down: son T1 T2. Now I could have written T1 and T2 as constants. As a matter of fact, I'm wondering why I didn't do that. Yeah, it doesn't really matter that much. But so T1 and T2 are two things that exist. There are some specific people that exist that satisfy all these things, right? So it's not true for all people, it's just true for some of them. So there exist some people for which all of these things are true. And so you can already guess if I say there exist some people with that, well, I can just write it down using this existential quantifier T1, T2. And perhaps this is why I wanted to write it with the existential quantifier, because as we discussed in exercise 4, whenever you have an existential quantifier, you just put an and here. And this is the sentence that you probably had in mind. Okay, and so that's how you construct this sentence. Let me look through some of the questions now. Isn't the symmetry already included in the given definition of sibling due to the bidirectional implication? Yes, that is true, but we haven't written it down explicitly. So we would need to add it to our knowledge base, but we haven't done so. You could do it, but yeah, we haven't done it. Why do we use an implication in 611? I think it was an equivalence, right? Not an implication. Yeah, it's just basically it's an implication in both directions. I mean, you can already see that here we have a universal quantifier, and with universal quantifiers you use implications and not ands, right? So that would be perhaps, yeah, to make the link with the other exercises. Is sibling only one direction? A is B sibling, but B is not A sibling. So yeah, it is like this in real life, but we haven't added this in our knowledge base. We would need to add this as well, but yeah, here for the sake of simplicity, we haven't done so. Because there's, I think, just one sentence that uses sibling, so it's not worth it adding that explicitly. I did not get the last one. Can you explain it again? So you probably mean this, right? So here you just analyze what people are involved. So you have that man's father. So that's one person. You have my father. which is another person, and then you just say, okay, what do we know about those people? We know about T1 that it is the father of that, because that's just what's written here, right? So we write this down. Then we have T2 that we know it's the father of the Mies person, so we write that down. And we know that T1 is the son of T2, right? Because we know that. And so we just write this down, and then we put an existential quantifier for all of it, and yeah. That was not intended, damn it. That's my mouse, and I need my mouse. So will it be possible to ask questions about logic exercise during holidays? Yeah, if you want to ask them on Moodle, go for it. Would be father T2, T1 instead of son T1, T2 also be valid? Yes, true, you could do that, but then for the next steps, it will be easier that way. I mean, that's why you can do it that way. That's why we had this inverse relationship, I guess. It will just take you longer, I suppose. But yeah, you can do that. Why do we use universal also for P in 611? 611. I mean, because it's true for every father and every child, right? I don't really know how to justify this better. I mean, basically you have here from every, and yeah, that's it. But why is the given definition of the knowledge base for sibling not symmetric? I mean, you can do that. It's just going to take you longer afterwards. You will see when we do the resolution graph, the way we did it is a little bit faster. You can also do it your way, but it's going to take you one additional step. Yeah. Why do we use an and not an implication in 613? 613, I mean, that's again the thing that if you use an existential quantifier, pretty much in no instance are you going to use an implication, and the and is always going to be almost always going to be the thing that you meant to use. It's, yeah. There are some counter examples. I mean, you can go back to exercise 4 where there are some counter examples, but yeah. Wouldn't it be that the relation between father and parents, that if a child exists for which P's are parents, to clarify my question, where is an universal quantifier used and not an existential quantifier? This is a little bit tricky to explain. I think I answered already a question like this on Moodle, and the answer was, if you only use an existential quantifier, for example, for the child, then the meaning of your sentence changes, because it means that for every parent, there has to exist a child that has this property, but that's not what we want. Okay, but this sentence does not make sense, that I have no siblings, but that my father is my father's son. Oh yeah, well, we'll see. So now that we have formalized everything, let me continue. This is my favorite slide, because it's a bit sad that I can't see your faces, because I am absolutely certain that I would see only confused faces here, because here I'm going to try to solve the puzzle informally, meaning without first order logic. Spoiler alert, you don't have to understand everything, okay? This is just how you would solve it, yeah, just with the sentences that we are given, right? So we have pretty much the sentence, and then is my, yeah, actually let me write it out completely. Didn't want to do that, but anyway, but that man's father is my father's son. So the important part here of the sentence is this part here, right? Because we know, okay, my father's son, right? So it's the son of his father. Well, it can only be either me, like the me speaker, or a sibling, right? Let me finish this slide, and then I can already see some questions, but I will answer them right after that. So me or a sibling, right? But the thing is, there are no siblings. So this means that my father's son, that's just the me speaker, right? So when we say that that man's father is my father's son, so is me in that case, because we can just replace it by me. And so he is basically the father of the man in the painting. So the person on the painting is the son of the speaker. And to write it in first order logic again, this would just mean son that me. Now, again, before I see questions shooting out here, this is not necessarily a slide that you need to understand perfectly or an explanation that you need to understand perfectly. It's just to give you an impression of, if you do it without first order logic, it might confuse you a little bit, because I'm sure there are going to be plenty of students who look at that and are like, Adrian, that's all fine, but I have no idea what you just said. I am totally not convinced that what you just said, that that is the son of me, is actually true. Please prove that to me. And that's exactly what we're going to do next. We are actually going to use first order logic to actually prove that the person on the painting is the son of the speaker. Now, why did I still go through the trouble of the slide? The reason is simple. If you want to do a resolution graph, right, you need to start with a goal. Like, you have to assume, okay, I want to show that this is entailed by my knowledge base, but you already need to have an idea of what you want to prove. Then the proof itself is pretty easy, but you need to start with a goal that you want to say, okay, I think this is true. Let's double check it if it's actually true. And that's why I went through all this trouble, because sometimes you really have to go through sort of heuristics or whatever to check if to check what is your approximate goal, what you think is going to be true, and then you actually use the algorithm to actually double check that this is actually the case. Okay, so let me go through the many questions. This talk is universal quantifier and the implication 613. I guess you mean for oh, for this one. Oh, yeah, I didn't notice that here I used an and. I mean, here you can't use an implication here, because, I mean, you are not implying anything. This is perhaps one of the only examples where I'm using an and with a universal quantifier, but yeah. Okay, and if you meant the other sentence, no, in that case, you would not be able to use a universal quantifier, because we are not talking about any father of that man, even though in theory, it doesn't make sense, right? Because there is only one father per person, but this would be something that you would need to define in your knowledge base as well. And that would take some time, and it would make everything much more complicated. So we are taking it easy here, and we are saying, okay, instead of using universal quantifier and creating universally correct rules, so to speak, we just say, okay, there exists some person that obeys this rule. How are brother and sister defined? Well, they are not. We only define sibling because that's the only thing that we need. We could also define brother and sister, blah, blah, blah. But again, this would make our knowledge base much more complicated. And trust me, the knowledge base is complicated enough. 613 mean I don't have brothers and sisters. If no, how would you formulate the sentence? I don't have brothers and sisters. Yes, that is correct. That's a correct formalization. Sorry, a correct sentence that fits to this formalization. In 613, the first question has universal quantifier. But why do we use and? Should it not be an implication? Well, I mean, that's what I said before. An implication basically just means that you imply something, right? But here, I mean, here there's nothing being implied here, right? And there's nothing like if A, then B. That's why I always took care to say when you use a universal quantifier, typically you want to use an implication. But that's important. That's typically, it's not always true. Sometimes you want to use an and. It's extremely rare. Yeah, I hadn't noticed that I used it in that sentence before. But yeah, here the meaning of the and is a little bit different, right? Because you just put the and so that you do it in both directions, right? That's basically it. I know this goes a little bit against what I said earlier, but yeah, that's why I was always careful to say typically, not always. This is one of the very few examples where you use an and not an implication. Okay, so now, as I said, once we have sort of our heuristic of what we want to show, right? Let's double check it formally. Let's mathematically prove that this conclusion here is actually correct. And to do that, we actually need to use resolution. And in order to use resolution, we need to transform all of the sentences to conjunctive normal form. So it works a little bit similar to propositional logic, where you have to take this with a lot of salt because there are going to be some important changes. So this elimination implication and moving the negation inwards, this is actually similar to propositional logic. There's not much changing there. This is new. Standardizing variables, this is actually new, but we are not going to use this in this exercise, as a matter of fact. It's still a very important aspect of transforming everything into conjunctive normal form, and it typically leads to errors, like many students do errors with that. If you want to see more details, you should look at slide it is 58, I think, no, 59. 59, lecture 8. There is an example of where basically you have two clauses which both have a variable x, but you have to be careful. Standardizing variables just means if you have two variables which have the same name in two different clauses, you have to see them as different variables, so as x1 and x2. There's also a post in the Moodle forum of a student that asked a similar question. Yeah, check that out. But we are not going to use this in this exercise because it just so happens that in this exercise it's not necessary. And as I said, standardizing variable. Okay, let me just write it down. Basically, if you have a clause AX and BX, something like this, and those are two separate clauses, right? Then you can basically see them as X1 and X2, right? Those are not the same thing, not necessarily, right? Yeah, that's pretty much it. That's true for variables. It's not true for constants. That's an important difference here. Okay, now I can go back to the rest. So then we have to do Skolemization, which basically means we want to get rid of the existential quantifiers, right? We'll see how this works afterwards. And then we drop the universal quantifiers. This is not strictly speaking necessary. It just makes the clauses a little bit easier to read. That's it. And then distributes the or and the ands. And this is just like propositional logic. Not much changes there. Okay, I think that still transforming everything to conjunctive normal form is always easier if we do it in practice. So let's do it with some of the sentences. We are not going to do it with all of them, as a matter of fact, because there are some which are just plain too easy, and I don't think it's going to bring you a lot. So let's deal instead with the complicated ones. So for example, this one. So the first thing that we need to do is implication elimination. Here we actually have a biconditional elimination. So we actually need to get rid of that one first. And how do we do this? Well, we just split it into an implication in the one direction and an implication in the other direction, okay? And we will deal separately with each part. So let's first start with that one, and then in a second step, we are going to deal with that one. So as I said, let's start with the direction left to right. And so the only thing that we need to do here is eliminate the implication. Just like propositional logic, there's not much to explain here. Yeah, to transform this with an or, and here you have a negation. Yeah, that's pretty much it. But we still have a problem. We here have an existential quantifier, and we want to get rid of that. And the way we get rid of that is by saying, okay, there exists a p, right? So I can replace this with a constant, right? But the thing is, so I'm going to replace this with a constant that is called f. But you can see that this p may potentially depend on x and y. So I actually need to replace it with a function instead of a constant that depends on x and y. But apart from x and y, this thing is constant, so to speak. And so I replace this occurrence here and this occurrence here. Okay, so let's see how this would look like if my pen decides to work. Here we go. So I have replaced here my p's, and now we are almost done. The only thing that still remains to be done is distribute here this or, and yeah, this is relatively easy, just like propositional logic. And then you end up with this clause, and this clause. Yeah, that's pretty much it. That's for the one direction. I see a question, there's no lecture tomorrow. That is correct. You only have an exercise class today, unless, I don't know, you want a lecture on Christmas. But yeah, we couldn't take an appointment with Santa Claus, so yeah. What does f for again, and why do we use it? So f is a sort of replacement. It's a sort of constant, more or less. I mean, it ends up being a function because you have a dependency on x and y, but it's a sort of constant that you use to replace the existential quantifier, because actually when you use resolution, you can't deal with existential quantifiers that mess everything up. So you sort of have to replace it with something just for the sake of the algorithm, let's say. So yeah, that's called a Skolemization. Okay, now let's go do the other direction, because as you remember, you had this biconditional implication in one direction and in the other direction. So now we do the other direction. And just for the sake of simplicity, I decided, okay, like it's in that direction, but let's switch it up so that it's something that we actually know. And also the brackets are here, by the way. So we just eliminate the implication, right? Because that's the only thing that we can do at this point. Let's do just that. Put an or here, and sorry, a negation here and an or here. Now we have to move the negation inwards. So this becomes an equality. And if you have the negation of an existential quantifier, then this is just the same as a universal quantifier and then the negation of whatever came here. Okay, so let's just do that. We have here a universal quantifier then, and then the negation of whatever was inside. Now that we have a universal quantifier, we can just plug it at the beginning, which is then going to give us this sentence, and then we are pretty much done, right? Because this is just one clause in conjunctive normal form, and yeah, that's it. Let me check the questions. I got a score in Artemis exercise 2. Does it mean I successfully submitted? I guess depends what you call score. Like you have to finish all the parts. How can we see which variable f depends on? Well, that's pretty easy. You literally just look at what quantifiers you have at the beginning, and that's it. Yeah, it's not necessarily a big deal if you add, yeah, although yeah, I'm trying to think what would happen if you use if you have to standardize a part. Yeah, okay, yeah, never mind. You just have to look at what quantifiers you have at the beginning, and that's it. Can you speak a bit slower and maybe go back to the last slide? Yeah, sure, I can speak slower. Just tell me what you call last slide here, because I'm not quite sure. I have a lot of slides now. Yeah, you can also write me later. But yeah. I mean, we're almost done with the exercise either way, but yeah. Couldn't we have also used the all quantifier to remove the exists quantifier in the first example instead of the F? No, you couldn't have done this. I mean, there aren't so many ways to replace quantifiers, right? So the only way that you can get rid of existential quantifiers is when you are lucky, like here, and you have a negation at the front, right? That goes inside and then it transforms your existential quantifier into a universal one. But apart from that, there's nothing that you can do to get rid of existential quantifiers. And so you can't, yeah, sort of get rid of the Skolemization. Yeah. Yeah. Also, perhaps one more thing. Exactly like for propositional logic, up to relabeling and reordering, blah, 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 the conjunctive normal form of a first order logic sentence is always unique, right? So if you see that I end up with a certain formula for the conjunctive normal form and you get a different one, then you have probably done a mistake somewhere, right? So yeah, you can always see it like this. If you see that something would be changing your conjunctive normal form, then it means that it's not quite, it's not an equivalence transformation. Let's put it like this. Okay, so CNF means terms potentially with ends, but no ors, connected by ors, not almost. Conjunctive normal form is like, I think the other sentence is a little bit easier to see. So it's basically like brackets where you only have ors, which are connected by ands. Okay, that's pretty much it. And you have no existential quantifier, and you have, yeah, that's it. And the universal quantifiers are all in the front. That's it. Okay, then let's continue, because I think we took quite a bit of time already. Then we have this sentence here. This is going to be very straightforward, because the only thing that we need to get rid of is here the existential quantifiers. So we are just going to replace this by big F1 and big F2. I mean, here there's no dependency on any universal quantifier, so we can just do that right away. And yeah, that's pretty much it. So we have this clause and this clause and this clause. That's it. And then we also have the goal, right? And just like we had for the Superman example, this just means that we have to add to the knowledge base. Whoops. Yeah, sorry, my template is not particularly good, but yeah, I hope you can interpret it too here. Adds to the knowledge base the negation of the goal, right? Which would be not son that me. Okay, and that's pretty much it. This then gives us this gigantic thing. And that is perhaps the point where some of you are going to regret those comments like, yeah, but why don't we define brothers and sisters, and also the fact that sibling is like symmetric and everything. Well, everything that you do makes this bigger. And I think that's big enough. Yeah, let's deal already with this knowledge base. And if you want to define some more stuff, then be my guests. But yeah, it then makes things much more complicated afterwards. So a more detailed knowledge base is not necessarily the best way to find a solution then. Anyway, so we want to use resolution. How do we use resolution? Well, I think the best way to explain this is by showing some examples, right? But basically the idea is it's the same as propositional logic, but you have to unify the sentences a little bit. So let's see what I mean by that. So typically it's typically a good strategy to start with the negation of your goal whenever you start a resolution. In that case, it's going to be not some that me. Also, by the way, for me, t is going to be that, and m is going to be me. That we took so much time. Okay, yeah, I'll do this a little bit quicker because yeah. And so again, in theory, you would need to check every possible clause that you can or cannot combine, but yeah, to gain some time, it's just that one. There may be more than one way to prove this, but let me just go directly to the solution there. Whoops, SP. Or not male S. Here we go. And basically, we want to combine those two clauses, right? How do we do this? Well, you can see that here we have a son and here we have a not son. Okay, so that's basically how we would do for propositional logic, right? But we have a little bit of a problem because we have here two variables, right? And here we have some other stuff, some constants, here we go, which may not agree, right? But we always assume that whenever we have a variable, there is always a universal quantifier attached. And that's perhaps also one of the reasons why we can't deal with existential quantifiers. With existential quantifiers, there might be some variable for which this, what I'm going to say next is going to be true. But if I have universal quantifiers, I can just choose my variables freely. So if I want to identify those two clauses, I would need to choose S equals T and P equals M, right? And if I do that, I then get the result, not child. And now I can replace all the S's by T's and all the P's by M's, or not male, T. Here we go. And that's pretty much it. That's how you use resolution for first order logic. You just unify, you just see what variable you need to replace such that it fits, and then you go from clause to clause like this. Now I can already see some people asking, why did you do it that way around? Why didn't you choose here here an S, here a P, and here no, it would be an S actually. Right. The answer to that is pretty simple. Those things here are constants, right? So I cannot change them. They are defined that way. And those here are variables. So I can change them. I can adapt them to the circumstance. I can adapt them to the clause that I want to compare it to, right? And so that's exactly what I'm doing here. And so I cannot choose general S and Ps anymore. But it has to be specific S and Ps in that case. Okay, let me go through this one question. 6.1 looks like a great exercise for the exam. 5 minutes should be enough to solve it. Yes, definitely, I agree. No, don't worry. For the exam, it will be much shorter. It's just to give you as many examples as possible of what you have to do for first order logic. Anyway, so then I want to combine it with this clause here, male that, and here it's a bit easier because I don't need to unify anything, and so I only have not child. My pen is not working great anymore, but we are almost at the end. Here we go. And then I want to combine it with, where is it? Here it is, this thing. So not parent PC or child, CP. Here I need to use unification again. There's not going to be a lot of space, but basically it's parent. And for the unification, let me put the bracket here. I'm sorry, it's a little bit short on space. So we need C to be equal to T and P to be equal to M. And so P we have M and T. that way around. Okay, of course, we're not finished here because we haven't ended up with an empty clause just yet. But basically, you would need to do another thing on the other side, and you would get to parent me that. And basically, if you take what we had before, this would be parent, not parent me that. And you basically combine those two things. This gives you the empty clause finally. And so this shows you that indeed the knowledge base does entail that the person on the painting is the son of the speaker. So yeah, this sort of settles the debate because yeah, you have proven mathematically that your assumption that you had at the beginning that we sort of came up with a little bit informally is actually correct. Let me go through here. What we deduced here is actually correct, and so everything is fine. Now again, what's the other thing that I didn't derive by myself here in this exercise class, it's the same tricks that we used here, right? It's just you have to use it again on this side, and it takes a little bit of time, and I didn't want to explain everything because it's not completely necessary to better understand first order logic. I mean, everything is said and done here, so yeah, it should be enough, I believe. So yeah, that concludes this exercise. If you have any questions, then now is a good time for it. I'll try to answer questions very, very shortly because I mean, Josefina has to give her exercise. I'm sorry I took much more time than I expected. But yeah, let me just see some questions. Is there an intuitive connection between the informal solution we had and the formal proof? I mean, a relation between the steps taken? Yes, there is, but it's a little bit hidden. I think it's, can't remember on which slide. No. I mean, you can see here that you have the fact that, okay, he doesn't have any siblings. I mean, there are some comparisons that you can make, indeed. But yeah, it's a little bit easier to see. Yeah, it's a little bit more difficult to see. Does this mean that we could extend the knowledge base with the results now? Yes, that is true. We could add this to our knowledge base, or could we say that we don't need to extend the knowledge base with the result as it is already entailed? Depends what we want to do next. If you want to show some additional results later on, then it might be worth adding it to the knowledge base. Otherwise, yeah. Okay, I don't see any other questions so far, so I would suggest I give the exercise class now to Josefina. I think some people want a 5 minutes break, but I think it's going to be a 5 minutes break anyway, the time that Josefina needs to set everything up. So yeah, it's your decision, Josefina, how much time you want to give them as a break.
Yeah, okay, so we can take a 5 minute break so I can get set up and you can mentally prepare for probability theory. So let's meet again at 5:08. Again, hi, thank you. So again, hi, I'm Josefina and I'll be doing the exercises on probability theory and hidden Markov models. You maybe already know me from the lectures. So we will start with the exercise 7, which looks as follows. So before I forget, I've uploaded some additional material for you. So this is on Moodle an additional material, a visualization of probability theory. So in hopes that this is a little more intuitive. It is still a work in progress, but it already covers most of the basics. So if you want to have a look, this might help understanding probabilities. Okay, so just a disclaimer, I don't have the iPad either, so it's not my fault. Adrian did not have it too. Okay, so let's start with the exercise. So we've got the first problem, which goes as follows. So consider the following probabilistic inference problem with random variables for driver expertise, road conditions, and accidents. The joint probability distribution is provided in the table below. So it's here. Yeah, and the values are guessed. We did not compute them. So the first variable is R, which describes the road condition, which can be dry, wet, or snow. And it is, yeah, discrete random variable. And the other variables are Booleans. So we have E, which indicates whether a driver is experienced, and A, which indicates whether there is an accident. Okay, so let's have a look. We have here the two Boolean variables. They can be true or false, so this is quite boring. And then we have the probabilities for R, so the different road conditions in those three columns. All this is a joint probability distribution. So let's recap. Okay, what is a joint probability? It is a statistic that calculates the likelihood of two events occurring together at the same point in time. So if we want to draw it using a Venn diagram, for example, we've got event A, and we've got event B. And this one, this area right here, is A and B. So this would be the joint probability. So this area is the joint probability where A and B occur at the same time. And we can calculate it with this formula right here. So just as a recap. And what's also important is that for the joint probability, the values always add up to 1. And we have a look at the entire universe. So at all random variables that are given, we look basically at the entire table. We look back, we look at this entire table. Okay. So for the first problem, as I said, the values of the joint probability distribution always add up to 1. And fortunately, there's only one value missing, this one. So it's quite easy to guess what we have to do. Well, we can calculate 1 minus all those entries, so the sum of all those entries. I just call it the rest, as I do not want to write down all those numbers. So this would be 1 minus 0.067 plus 0.3605, and so on. Basically, every number you got here. And this gives us the result, which is 0.1501. So this is the first task. I mean, you can calculate it again at home, but I will not write all of this down, sorry. Okay, let me check if there are any questions already. Okay, the audio is bad. I'll try to talk a little bit louder, maybe. My internet connection is a little interesting here. Okay, the additional stuff I said, it's an additional material on Moodle in the probability section. Okay. Why do we have the question mark? Well, because that's the exercise. We somehow lost this number and we have to recreate it. There's no real reason. It's just the constructed example. Maybe someone spilled their coffee on it or whatever. So yeah, it's just missing, and that's it. Okay, then let's continue to problem 7.1b, which is this one. Now, what we want to do now is a conditional probability. So what is the probability that the driver is not experienced, given that there is an accident and the road is wet? So we need to somehow write down this probability we want to have. Sorry. So we have to add up everything and then take 1 from it. No, not every row sums up to 1. So let me go back, or can use this one. All these values sum up to 1. So they sum up to 1. Because this is this table describes every possible event that can occur. And in our sample space, the sum of the probability of each event is 1. Now I throw out the old 7b. Okay. So basically, if we go back to the Venn diagram, we could say this table represents this entire circle. So everything, this is our universe U, and all those events in the table are contained here. There's an event that overlaps with this one, and so on. And therefore, we have to take 1 and subtract the sum of the probabilities that we are given from it, and this way we get the missing probability. Okay, let's go back to 7.1b. There we have what is the probability that the driver is not experienced, given that there is an accident and the road is wet. So this little word here, given, already tells us that we have a conditional probability. So is the probability for some she wet A not E? Not exactly. So it says we want a probability that the driver is not experienced. And if you read such an exercise or such a text, everything that comes behind given goes behind this sign here. So this means given. So that there is an accident and that the road is wet. So R equals W means that the road is wet. Okay, let's recap conditional probability, which is defined like that. So the probability of one event given the occurrence of another event is called the conditional probability. The conditional probability of 1 to 1 or more random variables is referred to as the conditional probability distribution. So, and we have this formula right here, which we can use now. Why do you write in small letters? I write in small letters because the there we are. The uppercase letters are for the random variables, and the lowercase letters are for specific events. So we want a specific event that the driver is inexperienced, and specific event that there's an accident and that the road is wet. So this is one special event, and the uppercase letters define the random variables. So this one. All right. Okay, what can we do now is that we use this formula, which goes like this. We write the probability of not E, that the road, no, sorry. That there is an accident and that the road is wet, divided by the probability for there is an accident and the road is wet. Okay. Let me quickly check the question. What do you mean with is that an A? What? Okay. All right. Also, what's important for conditional probabilities, I told you before. I told you before that for the giant probability distribution, we look at the entire universe that we are given. So this entire table, but for the conditional probability, we only look at a small part of this universe. So we have basically a new universe. In our example, this means we only look at a part of the table where experience is false. No, sorry, where accident is true. So this one and this one. And we want the road to be wet. So we are in this box right here in this column. And we only care about that there is an accident, which is kind of mean, but okay. So again, there has to be an accident. So we are left with this one and this probability. These are the only probabilities we need right now, as you will see. So we know the upper one. So no, let me. Okay, this stays the same, and we need to still somehow pull apart the this probability for accident and that the road is wet, which is the same as which is the same as adding up this value and this value. So, okay, for the next slides, I'll add some extra slides so I have more space. Okay, so what we have to calculate is basically 0.0654 divided by 0.0449 times 0.0654. Okay, the result, I wrote it down, is 0.5929. Okay, that's it. So maybe, sorry. What? No, of course not. Okay. Okay. That's for problem 7.1b. Yes, it should be plus. Sorry, it's a little late. Yeah, of course, we have to sum these two probabilities. So for that there is an accident, does exist twice. So probability for that there is an accident and the road is wet. Basically those two events, this event, and we sum those up in the denominator. Thank you for checking on me. All right. Any other questions? Could you also do it with normalization and sum over the hidden variables? Yes, I suppose you could, but it's mainly used for Bayesian networks. It would not really, it would be quite an overhead right here, I think. So you could, but yeah, but I wouldn't do it. So normalization we will do in the exercise 8 with on Bayesian networks. So we have Bayes rule, if you remember. I think I have it here somewhere. Yeah, there's Bayes rule. And this one is the so-called normalization factor. Normalization factor. So this little part right here, it takes care of the result being a probability. That means that the result is somewhere between 0 and 1. That's what probability is defined as. If we would leave this normalization factor out, we would only have a likelihood. So a likelihood is not really defined as being between 0 and 1, but it can be any number. But with the normalization factor, we normalize it to be between 0 and 1, which is way more intuitive and better to understand than some random values which you always would have to put into perspective. Okay. Okay, let's move on to Bayesian networks. There's problem 7.1c, where we are supposed to construct a Bayesian network with the conditional probability tables. Now, what do we have to do first? First, we have to think about which states are there. Now we have 3 random variables. We have E, A, and R. And let's check first which are dependent and which are independent. Now, E, the experience, does not depend on anything we have right here. And so does R, the road condition. However, the probability of an accident depends on both. So we can draw our network like that. An accident depends on the experience of the driver. So if the driver is inexperienced, it's more likely to occur. Also, if the road conditions are bad, of course, accidents are more likely. Okay. I've prepared this right here, so I do not have to write as much. Yeah. So we can see that E and R are independent, and A depends on E and R. Okay. So now what do we have to do? We have to calculate the as it's stated in the task. Let me reread the task. Sorry. Well, I mean, it's kind of in the joint probability distribution in this table, because if you look at experience and accident, you might have a look at those values. So there's an accident, and yeah, let's look at this. Let's say there is, they are not experienced, there is an accident, and the road condition is not too great. This is quite a high value, for example. Yeah, but it's more common knowledge. Okay, so for R, we will sum up all possible values. Yeah, just a second. We will start with E. So what would we have to do to get the value for E? Okay, what does it mean? Again, we look at instances where E is true. So this would be this one and this one, and sum up all the probabilities in this column. Write it down, which is then 0.6486. And as we stated in the lecture, we leave out the negative events, so P for not experience, as it's simply 1 minus PE. Okay, same now goes for PR. Here we sum over the columns. So we have 3 values. We have, we have the 0.65 for a dry road. And we get this probability by summing all these values. And yeah, for the other 3, it's the same. We sum those columns. It's every occurrence, every probability that can occur when the road is dry, wet, and or snowy. And so we get these values here. Okay, so far so good. Now, what we want to do is calculate these values. How do we have to do that? Okay, now, you should remember the chain rule. The chain rule is basically the same as the definition of the joint probability. So let me go back to that. There we are. So you can also call this chain rule. Some people call it multiplication rule. This rule has tons of names, but we will call it chain rule. Okay, let's go back. And using the chain rule, we can state that the probability of A, R, and E, so this is joint probability, can be written as P probability of A, given that the road has some state and E times probability of R given E times, times probability of E. So this is just this chain rule applied. Again, if you look right here, here we have it with 2 random variables, but you can of course expand it randomly to any other variable, number of variables. This is what we do here with 3 random variables. So this would be it. Now, in the Bayesian network, we thought about before that R and E, they are independent. So we can throw out this E and say that this probability is the same as E of R. So that means being independent means that the probability of the experience does not add anything to the result of P of R. So another example for independence would be tossing 2 coins. The heads or tails of the second coin does not depend on the result of the first coin. So therefore, it does not make sense to include it in our calculation. Okay. Now, accidents and experience are not independent. Accidents depend on experience, but the road conditions here and the experience, they are independent. So this is why we can remove this E right here. I'm sorry you lost all your money. Maybe you got cheated. Yeah. But now you can take it all back, I hope. Or use a fake coin or whatever. Okay, so now we can reorder this equation so that we have P of A, so an accident, given the road condition and experience, is the same as P A R, damn it, E divided by P road condition times the experience. So now this is the formula we need. And so I'll do it as an example for X1. So X1 means we have the probability of an accident. Again, this is a specific event. Now accident is true. Therefore, we write it in lowercase letters. Okay, let's go back. So that there's an accident. The road is dry. I just call it D, and that the driver is experienced, divided by the probability that the road is dry times the probability that the driver is experienced. For which we can now have a look at our table again. So keep in mind, we want the probability that there is an accident, the road is dry, and the driver is experienced. So there's an accident, we are experienced, and the road is dry. So that's our value, the first one. First one, so we've got, I forgot the value, 0.0706. Oh, 7, yeah. And now we divide it by the probability that the road is dry. We have this given right here. So it's 0.65 times the probability that the driver is experienced. We have this right here. So 0.6486, which I also calculated beforehand. And this is 0.144. Okay, let me look at the question. Shouldn't it be probability? Yes. No, what? Where do you mean? For the X1 calculation. No. I mean, we want, okay, so we want the probability that there is an accident. So this is the probability table for A. This is why we have A right here. Given the different other events. So given that the road is dry and that the driver is experienced. Therefore, we need the conditional probability. We want the probability under the condition, so the probability of an accident under the condition that the road is dry and that the driver is experienced. Okay. Yeah, no, we don't need the formula right now. But basically this is the formula from before. So this one, this formula is the formula of the conditional probability I showed you before, just with fewer variables. Okay. So for the other axis, it goes the same way. So I suggest you can do it by yourselves right now, because it's just putting the respective values for R and for E into this formula right here. So you put it in there. And then you can simply calculate it by looking at the table. And these values we have calculated before. So that would be quite repetitive, so we skipped it. And I think we are out of time anyway already. I did not expect this. Okay, let me check the questions again. Oh, thank you. That you like the way I explain everything. That's very good. Okay, please recheck the formula of 7.1c. Yes, absolutely. Okay, you're right. So yeah, you're perfectly right. Thank you. Sorry, I just did not see it. Just the line was a little bit too long. Yeah. Okay, so here's me sitting and telling you just put it in the formula and then you're good, and I cannot manage it on my own. Okay, thank you for thank you for this, for checking up. Okay, and then I would say have a Merry Christmas and a Happy New Year. And we see again next year for some more probability theory. May the probability of great presence be equal to 1 for you. All right, we can stop the recording and see you.